Hey everybody. In this video, we're going to talk all about manipulating bits in x86-64 YASM assembly within Ubuntu. But if you're not using YASM or you're not on Ubuntu, this video is probably going to be pretty useful to you anyway, because I'm going to talk about the basic concept of manipulating bits in various ways. We're going to talk about some basic logical operators like ANDing, ORing, XORing, and then we're going to talk about shifting the bits to the left and the right, and then we're going to talk about the difference between shifting without any respect for whether the number inside of the bits is an actual integer or whether we just consider them to just be bits by themselves, or whether we're actually respecting the bits as numbers. And also we're going to look at the rotation instruction. So first I'm going to explain this. I'm going to write it down in a pad, and then I'm going to show you a program that actually does it, just so we can prove that it all works. Okay, so for starters, let me open up a little notepad here. What the heck am I even talking about? Let me write this down because I forgot this on my first take. I spent like 5 minutes, blew right past the explanation of AND and OR and XOR because I forgot that that was supposed to be part of this video. We're going to look at AND, OR, and XOR, at least for now, and then we're going to look at shifting, and then we're going to look at rotating. Okay, so first off, what is ANDing? I've explained that in another video, but long story short, AND just requires that two bits that you're comparing against each other are both a 1 in order to receive a 1. And so any other pair, like a 0 versus a 1, or a 1 versus a 0, or two zeros, are just going to be a 0. So AND means both bits that you're comparing have to be a 1 in order for the result to be a 1. The OR is pretty easy. If either of the bits is a 1, then the result is going to be 1. So if I say 1 versus 1, the result is going to be 1. If I say, 0 versus 1, the result is going to be a 1. Or if I say 1 versus 0, the result is going to be a 1. In the only case where you end up with a 0, it's just going to be 0 versus 0 results in a 0. To upgrade to exclusive OR, basically exactly one bit needs to be a 1. And if 2 or 0 are a 1, then the result is a 0, which means here when we have the two 1s at the top, the answer is going to be a 0. These other two stay the same, and this one stays the same. So that's XOR. Again, I have another video where I explain this a little bit better, but I'm just doing like a quick overview. Shifting is pretty interesting because let me do a pattern. Let's say 0, 1, 1, 0. Suppose we just have 4 bits. I could shift the bits to the left or to the right. So imagine left, if I shift them to the left, then what I'm really doing is I'm just taking off that 0 on the end and padding on the right with a 0. And then if I'm shifting to the right, then, well, it's to the right. I'm just going to, take off, let's see, the 0 on the right side and pad with the 0 on the left. Be careful though, because what I've actually done is bitwise or logical shifting. I haven't actually shifted with respect to the original number. Think about this. That number right there on line 3, if we just consider that an unsigned integer or just bits, then what I just did with the shifting is fine. But what if that was a 2's complement number that can represent a signed integer? If it's 2's complement, or if it's just like a signed integer, then the leftmost bit being a 0 tells me that that's a positive number, right? But if I look at the result of my left shift, there's a 1 now in that first position, which tells me that's probably a negative number. We could face a similar problem with shifting to the right. I mean, we didn't this time. It just looks like it actually shifted and the answer is going to end up being right. But what if we shifted something else right? Let's see. What am I going to do here? 1, 1, 0, 0. What if I shifted that number 1 to the right? The answer would be 0, 1, 1, 0, right? But then that's wrong because the original number was negative because there's a 1 in the first position. But the result is a 0. So if I'm not careful about what instructions I'm using and how to respect whether the number I'm shifting is actually considered an integer, a signed integer, or if it's just bits, if I don't respect that, then I could end up ruining the number. So keep that in mind. We're going to do several examples of that. I'm not going to show you how to actually arithmetically shift by hand. I'm just going to show you what the instructions in the assembler will do. So then the other thing that we should talk about is rotating. So imagine that I rotate this number 1 to the right. Well, nothing really happens visually, but what you're supposed to do, if we rotate to the right, you take the number on the very right side and you just pop it onto the front. So it's sort of, it doesn't fall off and get replaced by a 0 or get replaced by a 1, depending on what you're doing. It actually moves to the other side. So if I shift this again, maybe let's shift it one more time to the right. I'm going to take that 1 and pop it off the right side and put it on the very front. So see, do you see how it's kind of rotating? If I do this one more time, actually, let me copy paste this. I'll take that number on the right side, pop it off, put it back on the front. Then if I do it again, take that 0, pop it off, put it back on the front. Notice how it eventually gets back to the original pattern. And I would have to rotate, exactly 4 times to get that to happen. Same thing applies for rotating to the left. I'm not going to show you because it's the same thing as rotating to the right, just in a different direction. One thing that I forgot to say a moment ago when I was talking about shifting is think about this. If we shift to the right, pretend that we don't really care that much. Let me put some extra zeros here so that we don't have to carry too much. We don't have to care too much about what's happening with positive or negative. If you know how to convert to binary, which I've explained in other videos, then you'll know this number is, let's see, there's a 1 and a 2, and then these positions are 4 and 8. So this should be a 12, right? If I shift this to the right, I should be dividing this by 2 because the base of binary is 2. So every time you kind of like move to the left in terms of what digit you're looking at, you're increasing the power of that digit by 2. Every time you move to the right, you're decreasing the power of the digit by 2. So that means if I shift the entire thing to the right, I should be dividing the whole thing by 2, right? Not just one bit. So if I just take a 0 off of there and put it on there, I've now shifted all the bits 1 to the right. I should end up with a 6. Let's just compute what it is. There's a 1 there, and there's a 2 there, and there's a 4 there. What's 4 plus 2? That's 6. So this is actually 6 in binary, or the original number divided by 2, because we shifted to the right. On the other hand, if I take this number one more time and just kind of shift it to the left, I should multiply it by 2. So that means I should expect to see a 24. Let me just remove one of those zeros and put it on the right side there. This is not a rotation. I'm just kind of like filling in zeros. I'm keeping it simple with an unsigned integer. So if we look at the positions on the shifted number, this is a 1, a 2, and a 4. Again, if you don't know how to convert from binary to decimal or back, see my other videos. So then we basically have an 8 here and a 16. What's 8 plus 16? That's 24. 24 is twice of 12, so we have multiplied by 2. So you could multiply by 4 by shifting twice, multiply by 8 by shifting 3 times, whatever you want to do. But shifting is like a shortcut. Besides just to move the bits, it's also a shortcut to multiply and divide by 2. Okay, so that's the basic idea. Let me start working on a little program here for you. Before I continue, I just want you to know that my program, it's got stuff in it already. We've got a makefile here. If I edit the makefile, I just have a makefile set up to build the program. So again, this video is specific to just, bits. We're not going to talk about makefiles. See my other videos if you want to know how to make your own makefile. Same thing for this gdb.txt file. I've just put commands that I'm going to send to GDB, my debugger of choice. This is not a GDB video. I haven't actually made my GDB video yet, so look out for that in the somewhat near future. So we're just going to focus on the actual program for now. Anyway, so I've got a solution already set up here. Let me start copy pasting some stuff in there. Going to copy paste my data section. So first off, my sample program is just going to have codes for writing, with the system call and exiting with the system call. And then I'm going to output to standard output, and I'm going to do a 0 return code. If you don't know that, see my other videos that I've already put out. I'm going to make a sample string where I just say, hello, my name is Gibson Montgomery Gibson. That's not my name, but I love those names. I'm just going to say hello basically when the program starts. Then I have some bit strings here that will help me with help me demonstrate some of the bitwise operations, the ending and the ORing and the shifting and whatever. And then I'm going to put a negative number here as a variable just to prove to you that sometimes the bitwise or logical shifting will break a number if the number is supposed to actually be a signed integer, and use that as evidence for why you should use arithmetic shifting. So now I'm going to start my program here. Let's see, my entry point should start at line 30. I got to be super careful about this, because if I don't, no, it's 26. If I don't, then all of my debug statements are going to have to be adjusted, and that's going to take time on camera. Okay, so I think I got it lined up correctly. So I'm basically just going to print the hello message, and then maybe, you know what, at the very end, I'm going to exit from the system with a system call. So basically, if we run this program, again, system calls and everything like that are not part of this video. See my other videos, but if this works, we should see just like a simple message. Okay, so that's it. My name is Gibson Montgomery Gibson. Okay. So then the next thing that I'm going to do is I'm going to show you a bitwise AND operation. So I'm going to copy paste that. It should start on line 42. Man, if I get this wrong, the debugging is going to be awful. I was trying to make this a pure assembly program without a bunch of extra work. I guess I could have linked GCC so I could just print results to the terminal, but whatever, too late now. So it starts on 42 and ends on 51. Okay, so I think that's good. So the instruction for ANDing, doing a logical AND between two registers, which are full of bits, and then what will happen is every bit gets ANDed against its own against the corresponding bit in the other register, is just AND. So what I'm doing first is I'm going to set up the registers. So I'm going to move the A sequence, which if you look up is just, you know, I put a bunch of bits. So like in hex, I like to type hex more than binary when I'm just kind of putting stuff in there. So, you know, each F is basically 4 ones. So it's going to be like, I guess, 16 ones and then a bunch of zeros and then, you know, a few ones and then some zeros and ones. So I'm just making a little pattern for bits A. Don't think that they mean anything right now. And I'm going to make a different pattern with bits B. And when we look into the debugger, we should see the before and after patterns, so we can kind of see what the AND instruction did. So I'm going to move bits A and bits B into R10 and R11. Then I'm going to move, so these are going to be like the original bits that we can inspect later. Then I'm going to move R10, the original A pattern, into R12 so that I can place an AND on R12 with this AND instruction against R11, which is the B pattern. So I'm basically taking the A pattern and I'm ANDing it against the B pattern, but I'm also loading up the registers so we can see the A pattern, then the B pattern, and then the result of ANDing them together. Finally, on line 50 here, I'm using a nope, which is just a non-operation, so that I can easily break the debugger so we can sort of inspect the program and see what's going on inside of there. You know what? Let me open this up again here so that I can control where I'm breaking. So 48 is where the nope is. That's totally wrong. I've already ruined my program somehow. So it's gonna be 50, I guess. All right, 50. And what I'm doing inside of this, and again, this is not a GDB video, I'm just saying, let's break at line 50 so I can kind of poke around. And I'm going to comment all these things out for now. That's going to happen at the very end. It's going to be majestic how many different things we can look at. So I'm telling GDB not to execute any of these instructions except for the breakpoint instruction, so we can just break on line 50. Okay, hopefully this works. I'm going to now use make debug, which under the hood is just going to be compiling and then telling GDB to launch with the name of my program inside of it, and then to execute those things. So it hits breakpoint number 50. There's a bunch of crap that gets printed, and I can now inspect my registers. I'm going to go info R for just info registers, and let's see. So we had R 10, 11, and 12. So if we look at the terminal, you can see that R10, the hex version, has the original pattern of the A sequence, and then R11 has the original pattern of the B sequence. If we do a logical AND and put the result into R12, then you should see, let me just double check that that's definitely R12, yeah. Then you should see the result of ANDing all of the F's together. Remember that an F is just 4 ones, so I'm kind of simplifying it a little bit. You could make yours more complicated with lots of randomness in your ones and zeros just to prove it to yourself, but Notice how R12 only has an F where there was an F in both of the patterns up above. So like FF means F, F0 means 0, F0 means 0, and so forth. 0F means 0. So only where you see two Fs will you see an F in the final target pattern. So that's a logical and that's how you do it in YASM assembly. You just load up a register with some bits, R12, we loaded them up with the first pattern, and then we take the second pattern and say that's what I want to AND it against, and you can have that in a register, or I think an immediate, or a memory location. So we're just ANDing these registers together, and you know that they're loaded up with patterns A and B. So nothing too hard at this point. Let's look at bitwise OR. This should start on line 52, or I'm screwing myself. 52. Okay. 52. So same thing, we're going to load up R10 and R11 with the bit patterns, and then we're going to move the first bit pattern into R12 so that we can OR it against the second pattern. And so basically R10 and 11 will have the original bit patterns. R12 will have the result of ORing them. Then we'll do a nope on line 60. So I want to break here on line 60. Yep, I ruined all my line numbers. What did I do wrong? I think I just have it offset by 2 now for some reason. So if we just kind of run the program now in the debugger again, I'm going to do quit and then yes. If we clear and make debug, probably clear was unnecessary. We're broken at line 60. If I say info registers, the registers in question are, oh shoot, 10, 11, and 12, right? So we look at 10 and 11, they have the same pattern as before, and 12 has a lot more Fs because if either of the patterns had an F, then the resulting pattern would have an F. So this is a logical OR. Same idea as AND in terms of the way you format the instruction and the ops, but it ORs instead of ANDs. Okay, no problem. Let's move on. Next thing I want to show you is the XOR, which is pretty cool. By the way, so far we're just operating on bits. We don't consider these bits to actually be numbers. Maybe they are, but we should probably be careful about that. Anyway, so I'm going to say, let's check out our bitwise XOR, which is exclusive OR, which means exactly one bit in any pair needs to be a 1 for the resulting bit to be a 1. And of course, per usual, all bits will be checked against each other in the pair of bit patterns. It'll be 1 bit at a time from each pattern that gets checked. Okay, so it starts on 62, and then we got a nope there. Okay. So same thing that we did before. We're just loading up 2 registers with the bit patterns, and then R12 is going to be the result of exclusive ORing or XORing the 2 bit patterns. So that means we're going to break on line 70 now. Let me just get rid of my other breakpoint, change that 68 to a 70. And now I should quit. And if we do make debug, we're at 70 good info registers. So I think we said it was 10 and 11 had the original bit patterns. And notice the resulting bit pattern. It only has an F in a position where there was exactly 1 F between the 2 input patterns. So, wait, did I just do something wrong here? What did I just do wrong? Hang on a second, I'm seeing something bad. XOR R12. Am I looking at R12? Yeah. R10 and 11. Did I just do something wrong? 10 and 11, and then we load 10 up into 12, and then we XOR it by 11, and then it stores it in 12. Something's a little fishy here. Exactly 1. Exactly 1. XOR, I don't like that. What's going on? Oh, I understand now. Okay, so that was a little scary. This is shifted because the printout is not great. See how there's like a blank space here? That threw me off. So you have to imagine that all of the bit patterns are kind of shifted. Maybe I should just copy paste this. I was worried that I suddenly didn't know how to do an XOR in assembly. So let me get rid of these integers here. See, notice how there's just a blank space. That shifted everything and threw it off in terms of the display. So I'm going to do this. And what should really happen now is that there should be a 0 here. A 0 at the front. Now everything would make more sense. Sometimes the display likes to just kind of truncate things and just assume that everything will be read correctly, but it wasn't. So notice in the first position, both the input patterns are an F. So the output pattern will be a 0. You can imagine under the hood, there was a bunch of 1s and then a bunch of 1s, and that resulted in a bunch of 0s. Here we've got like an F and a 0, so the result is going to be an F, and then an F and a 0, and F and a 0. 0 and an F is an F. And then where you see 0s, that means there was not exactly one 1 in each bit position. So for let's see, the first one, that's a bunch of 0s for both input patterns, so that's why there's a 0 there. Then for the next two, each of them had all 1s or just the 2 Fs. So that's why XOR says it's a 0, and so forth, right? So like at the end, 2 Fs make a 0. Okay, that was a little scary. I'm glad I figured that out quickly instead of taking a million years. Okay. So now let's do another example. We're done with XOR. Now let's look at bitwise NOT. I forgot to explain NOT. I'm not going to redo this video. But let me just say that a NOT is just inverting the bit. So if we have a 0, it becomes a 1, and if we have a 1, it becomes a 0. And if you NOT against a register that has lots of bits, or a memory location that has lots of bits, you can do that, and just every single bit in the sequence will just be flipped from a 0 to a 1, or vice versa. So let's see, we just did bitwise XOR. Now we're going to do a NOT starting on line 72, I guess. And then we're going to do another nope there. So 72. Okay. All right, so now let's get rid of the breakpoint at the line 70 and put it at line 78 instead. 78. Oh man, this video is going to take forever. Okay. So now let's check out bitwise NOT. We're going to have R10. Oh, I guess I should improve this, because what I'm doing is I'm moving everything into R10, and then I'm just NOTing R10, so we can't really compare R10 against itself. That's not fun. Let me instead move R10 into R11 so that I can NOT R11, so that we can see two different registers at least. Okay, so let me just update my solution real fast. 73. Move R11, R10. Okay, so now it stops at 75, and that one stops at 75. Okay, cool. Now we got our breakpoint. Should be at line 79, not 78. Now we're ready to run it and see what the NOT does. Clear and make debug. Info registers. So we should have R10 and R11. Again, the formatting is a little wonky because there are missing zeros. So I'm just going to copy paste it up here. I'm going to do this, get rid of the numbers, pad on the left for the missing zeros, and then now you can see clearly that all of the Fs were flipped to 0. Again, that means, you know, each F had 4 1s inside of it, so all those 1s were flipped to a 0, so that's why it's a 0. Okay, so NOTing, pretty easy, not too bad. And then I'm going to quit this and show the next example, which was going to be, let's see, 79. Let's check out bitwise rotation. I'm going to copy paste all the way up to that nope there. Should start on line 81. I paused before I took a drink of water. Hopefully I reminded myself later to edit the drink of water out. I don't know. Maybe you'll be wondering why my mustache is wet right now. I did not edit it out. Okay, so let's check out bitwise rotation. So I'm going to set up our 10 and 11 and 12 and 13 and 14, all with the A pattern. And then I'm going to start rotating things. So first I'm going to rotate to the left, R11, and then R12. I'm going to rotate by 1 position on R11 and then 2 positions on R12. And then I'm going to rotate by 1 position for R13 and then 2 positions for R14. So we should see some interesting patterns. The nope is now on line 94, so I'm going to break there instead. Whoops. So I'm going to change that, and I'm now off by 3. It's getting precarious. And then I'm going to uncomment all of my little print statements to show you the value of the registers after I rotate it. So we should see like a bunch of stuff get printed in the terminal. just to prove to you what's going to happen. Okay, so, man, I got to remember what's happening now. First thing that I did was I printed R10 to show you one type of rotation, and then I printed R10 again to show you another type of rotation. So we should see the original, and then the two rotated values, and then the original again, and then the other two rotated values. So here's the original. We're printing it in binary with the special print command in GDB, which is just like P/T, and then the register. So this is the original pattern right here, and if you just kind of squint at it for a while, you can realize that the $2 pattern has been shifted once to the left. Actually, let me just make sure that I'm doing a shift and not a rotate. I'm accidentally saying the word rotate, I think, and that's... Oh, no, it is rotate. Yeah, we're going to shift later, I guess. Okay, so we are definitely rotating. So we should see some wraparound. I guess I used bad bit patterns for the wraparound, but just imagine that, you know, in this pattern right here, this one, if we're rotating to the left, this one fell off and it got placed on the right side of the next pattern. It's going to be the same thing basically. But this is rotation, so we would be reusing the bits that fell off. But anyway, you can see that if I rotate it to the left by one position, that whole thing is kind of shifted to the left. I shouldn't use the word shift. And then for the second pattern, we did a rotation by two positions. So all the bits are just kind of moved to the left compared to the very first pattern. Okay, so no problem. Then the next thing that we're looking at is just, you know, rotating to the right, and you can tell that everything is offset by 1 here, and it's offset by 2 here. So rotating to the left by one position, by two positions, rotating to the right by one position or by two positions. That's rotation in a nutshell. Okay. So then the next thing that we're going to do, we're on 94 now. I'm going to grab some logical shifting code. Let's see, logical shifting. Nope. I'm going to grab some code that will shift both logically and arithmetically, so we can kind of see the difference. Okay, so maybe I should change this to show some shifting. Because if I just say it's logical, then yeah, sure, the shift function, the shift instructions here, SHL and SHR, those are logical shifts. But then down here, when it's SAL and SAR, those are arithmetic shifts. I don't know, maybe I can do that. Maybe I can just duplicate the comment maybe to make it more intuitive. So show arithmetic shifts. And I'll just take that out. Okay, I think that looks pretty good. Let me paste that into 105 on my solution so I don't get out of sync here. So what's going to happen here? We're basically going to load up R10 with a negative number. I've chosen the number negative 12 because I kind of feel like it at least shows you a little bit for dividing and stuff like that. So we're loading up R10 with a negative number. And then R11 is going to get R10. But then we're going to shift it left by two positions. So that should be multiplying it by 4. But this is, well, a bitwise shifting, so it's not going to necessarily respect the fact that the number is in 2's complement. So this is not a good idea if you consider R10 to be a number, because sometimes the result might be right and sometimes the result might be wrong. Here it says math won't work in my comment, but sometimes it will accidentally work, but you still want to consider it to be non-working for integers. It's only good for bit shifting. Then we're going to put R12, we're going to give it the same value as R10, and then we're just going to shift it to the right by two positions. This will definitely break, because when you shift to the right, the sign bit is going to get padded with a 0 rather than what the actual sign bit was originally. So that will almost certainly break it almost every time. Then we're going to use arithmetic shifts, which just respect the fact that the original number is 2's complement. So, you know, like we have this negative 12 number. It's going to end up being bits, but the SHL and the SHR instructions are not going to respect the fact that it's negative 12. They're just going to consider them to be bits. But the SAL shifting to the left arithmetically and the SAR shifting to the right arithmetically, are going to respect that, respect the fact that it's 2's complement. So let's see, we've got all this stuff, and then we've got a non-operation here. You know, again, like per usual, when we're shifting, when we're rotating, when we're ORing, ANDing, whatever, it's just the instruction name followed by both the source and the destination operand, and then the second operand is only going to be source. So if we have shifting left R11, then the result is going to be stored in R11, but it's going to take as the source R11 and shift it to the left by 2 positions, and so forth. Okay, so we have all of that. We're going to nope on line 114. So that means I'm going to stop breaking on 94, and I'm going to break on 114. I thought I was 4 lines off, and now I'm only 2 lines off. I think I just did something else wrong here between my source. Let's see, is the nope on 114 up there? Yeah, it is. Okay. Guess I didn't do that much wrong. Okay, so let's run this, but this code up here was just going to print bit patterns related to our rotations. I don't really want that anymore. So I'm going to uncomment all of these other prints that relate to our shifts. And this is going to be a nightmare to read and interpret, but I'm going to try. I really should have written a more complicated program that can just print them in the terminal, so I don't have to like read the debugger. Whatever, it's brain exercise. And I think this actually is the end of the program. 119 is the last line. Yeah, okay, so we just need to run this and see what happens. So really we're interested in these, you know, shifting to the left twice, shifting to the right twice bitwise, and then shifting to the left twice arithmetically, shifting to the right twice arithmetically. Okay, so I'm gonna go back to the terminal here, I'm gonna quit, and then I'm gonna do make debug, and now there's a bunch of junk. Here's the original number, and then we're gonna bitwise shift left binary. Notice how it just sort of, it shifted everything to the left. And, we're not printing hex anymore because I want you to see the binary. And then, like the patterns are just shifted 2 to the left. Like, see, here's the first one if we're looking at the right side. And then here is the first one if we're looking at the right side for the shifted version. Notice how it's 2 positions to the left. Similar deal for shift right, except we lost a couple of numbers there because of the display. So I'm going to copy paste both of these real fast. Per usual, we lost numbers due to the display. So I'm going to say, notice how we have 2 numbers missing here. If I added zeros on the right side, that's going to change the actual value. So I'm going to have to add them to the left. And now we can clearly see that the original pattern here was shifted 4 positions, I think, to the left. Wait, did I do that? Where did I even just copy paste from? Original, shift left, and shift right. Okay, so shift right is what it's supposed to be doing. Let me just double check here. Shift right is printing R12, and what does R12 have? It has shift right by 2, so it should have 2 positions shifting right by 2. Okay. Oh, I'm supposed to compare it to the very first one. Let me just double check that I have this correct now. Why is it shifting to the right? Oh gosh, I think I just lost track of myself. Let me just, give me a second here. R14. I'm forgetting where I copy and pasted. Okay, bitwise shift right is bitwise shift right is R12, not R14. Oh gosh, did I do it wrong? Were you cringing at home? Bitwise shift right is R12. I'll do this. Maybe this will work. And then 2, that's kind of the same thing that I did before. No, it's different. Okay, so I had it wrong before, now I finally have it right. So you can see that the bit pattern is shifted twice to the right, and then on the left, 2 zeros show up, which would have destroyed a number. Okay, so we shift it to the right, and now we're ready to look at arithmetic shift to the left and right. And let's see, do we have enough bits to actually print everything? This one should look like it's shifted to the right just because of the way it prints, so that means this one is totally lined up. Okay, so let me grab the original pattern here. So this is the original pattern, and then if I go shift left in binary, I'll just put an L here. And then I'll put shift right in binary there. We have enough bits, I think, in both cases, so we don't have to pad. So now if we look at the original pattern and then we shift left arithmetically twice, notice how it does kind of look like it survived, right? Like this one moved over to the left twice because the sign bits are just kind of falling off, but there's enough of them that it's not going to change the sign bit. Thank you, 2's complement. But when we shift to the right arithmetically, normally we would have padded on the left with zeros. Remember we had zeros there on the left before, but now that we're respecting the arithmetic, the padding is correct now for 2's complement. So that's why there are ones there instead of zeros. And then if you kind of look at it, it's like, well, we shifted twice to the right. Let me get rid of the left because we already understand that now. It seems to be that the pattern is every bit is shifted over to the right the correct number of times. The zeros dropped off the side, and the sign bits were padded on the left. So everything seems to be correct. And then just to kind of prove to you that what we're seeing is real, I just have the same things printed all over again from scratch in decimal. So originally we had our R10 as -12, and then if we do a bitwise shift to the left, it multiplies it by 4, and so we're accidentally correct here. Remember, this is a bitwise shift, so it doesn't respect 2's complement. So just, you know, by pure chance, we happen to have a starting number that would end up looking correct after we shifted it to the left. And then when we do a bitwise shift to the right, again, this could be disaster because we're not respecting 2's complement or the sign bit, and that's exactly what happened. You know, definitely if we're shifting to the right, that should be 12 divided by 4 equals 3 or -3, but instead we get this gigantic huge number because the sign bit got killed with the zeros that were padded on the left. And then we finally try to shift left arithmetically. We end up still with -48, which is the correct number. If we're going to shift left twice, that's multiplying 12 by 4, and that's 48 or -48. And then when we shift to the right, that should divide it by 2 twice, because we're shifting to the right by 2 positions. So that should be 12 divided by 4, which is -3, or sorry, -12 divided by 4, which is -3. So everything seems to be working, except for a couple of moments of stumbling on my part, which I hope you laughed at. And I think this is the end of the program. So now, hopefully you're an expert in ANDing, ORing, XORing, NOTing, shifting left and right, bitwise shifting versus also arithmetic shifting, and also bitwise rotating. We've done it all in this one video. How long did this video take? 40 minutes? Anyway, thank you so much for watching this video. I hope you learned a little bit of stuff and you had a little bit of fun. I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video. and enjoy the cool music as I fade into the darkness, which is coming for us all.